Okay, welcome to the second part of ME 261. My name is Koushik Viswanathan. I will be handling this part of the course on differential equations, mostly on ordinary differential equations, and we will say a few things about partial differential equations as we go along. My contact information is as follows. My name, of course, is, in case you don't know who I am, that's my name, and my email, if you need to get in touch for whatever reason, is just my first name, Koushik at IISc.ac.in. Please write an email to me if you need something very desperately, or otherwise for anything that's related to the content of the course, I would recommend that you use Piazza, which I believe you guys have already been using for the linear algebra part at least. And under usual circumstances, I would give my office number, but that's kind of superfluous right now. But nonetheless, there is a phone in case you wish to use it. It's 2670, so there will be 2293 2670 with 080 if you're calling from outside Bangalore. And yeah, you can just use one of these modes to get in touch if you need any assistance of any kind, which the TAs cannot help you with. If you feel that you have to get in touch with me, then please do so via these means. Okay, good. So I'll be talking about differential equations. Now, I was told multiple times, I've been teaching this class for, this is the third time I've been teaching it, and every year I get reminded by several people that differential equations is actually part of the GATE syllabus, and that several students in the audience are presumably well versed with differential equations, and that they've done some form of differential equations before, ordinary differential equations, and some PDEs too. But nonetheless, in what I'm going to cover, I will assume that you've seen a differential equation before and you know what a differential equation is. Well, that's a starting point. If you don't know what a differential equation is and you're still sitting through this course, I really appreciate your courage. But we will start from the basics, of course, but we will sort of run through them, assuming that there is some familiarity. The book, well, I'm not going to follow any book. I don't usually follow any book because it's a little cumbersome to follow a book in a class when you can just read the book by yourself. So, but nonetheless, there is a book where most of the information I'm going to present is contained. That book is Elementary Differential Equations and Boundary Value Problems. It's by two people, Boyce and Di Prima. It's a very classical textbook, must be in some high numbered edition like 10 or 11 or something right now. It's been around for a long time, and it's a very standard treatise. And there is another book which is probably not mentioned in the course syllabus, but it is a book that's worth reading, especially on the nonlinear stuff when we talk about it, which is called Nonlinear Dynamics and Chaos, okay, by Stephen Strogatz. I highly recommend you read through the second book in particular. The first book can be a little bit dry, and the second book is highly recommended because it just draws on applications from all sorts of completely unrelated and bizarre sounding domains. And there are things about chemical reactions, there are applications to biological systems, to populations, to viruses, which seems to be a thing these days with virus modeling and stuff. But yeah, there's a lot of stuff in that book. So if you get a chance, please look at that book. I will discuss some of the nonlinear stuff loosely from here. Of course, it's a big universe by itself, nonlinear dynamics, and so we really won't be able to do much justice to it. But in the limited time that we have, we'll try to see how much we can cover. Okay, that's the whole point. Good. So excuse me. The idea is as follows. We have roughly 10 lectures. Okay, lectures come in integers. So either it's 10 lectures or 9 lectures or 11 lectures, but we'll assume it's 10 nominally. and I will not take the usual route. So, for instance, if you go and look at this elementary differential equations book by Boyce and de Prima, there's a standard way of presenting this material that will be like, okay, first order system, then there's second order system, and then there is higher order system, they're all linear systems, then homogeneous, non-homogeneous, and then what do you do if you have a non-homogeneous system, and then finally this non-linear stuff is sort of just thrown out there so that you know what is going on. Okay, that's the usual approach in a differential equations course. Of course, that approach is designed to last for an entire semester, so about 30 classes, and since we don't have 30 classes at our disposal, and since that approach has been going on for a very long time and we want to try something a little bit different, the route I'm going to take will be a little unconventional. Of course, all the material that is covered in these classes will be either here or in the notes. So, I will provide notes periodically on the material that I cover, and there will be assignments. Okay, again, nothing is going to change from the first part. There will be several assignments. I would think about 4, again nominally, could be 3, it could be 5, but that's what we're considering. And there will be a quiz, again just like last time when you had for the linear algebra, you will have a quiz, in class quiz, 10 or 15 minutes, just to make sure that we're all on the same page, you know what the hell is going on. Okay, and at the end of everything, we're going to have the second midterm exam, and we will the second midterm, of course, this is midterm 2, and that will focus exclusively on the differential equations part, and presumably will not have anything explicitly relating to the linear algebra, but as you will see, differential equations, the theory of differential equations builds on our understanding of linear algebra. So, linear algebra has to be sort of a prerequisite. You have to make sure that you understand linear algebra well enough before you can embark on any reasonably serious study of differential equations. Okay, so that's the plan, and like I said, all the contact information is here, and of course there is also Piazza, so ask questions. Okay, so we'll follow the same format that we've been doing so far. We'll have Monday, Wednesday lectures, and then we'll have a Q&A session on Friday. This Friday there is a midterm exam, I'm told, so I presume most of you will be busy cramming for the midterm exam, though that's not highly recommended, but still. So we'll start with the discussion stuff from next Friday, and we'll keep it going every week. Okay, that's what we're going to do. So about another, let's see, 2 lectures a week, that gives us about 5 weeks. I hope this information is clear. Please tell people who are not here, who are busy cramming for the midterm, about this information so that they don't miss out. Okay, good. So let's start right at the beginning. Okay, there should be a beginning to every study, and I suppose the beginning to this study is not different from the beginning to any other study, which is by asking the question, why on earth are we studying this in the first place? Okay, why? Why are we studying differential equations? Okay, that's the question that we should really ask, so that it sort of motivates us to study the subject, and it also gives us, you know, the hope that what we're going to do, what we're going to spend the next presumably 5 weeks on, is of some use at the end. Okay, this question can be sort of, notice I've said differential equations, so this question can be cast in a very general framework. I'm not saying ordinary or partial differential equations. The reason we study differential equations is because, well, there is one overarching reason above everything else, which is that all fundamental physical laws are expressed as differential equations. Okay, all. If there is a law that is not a differential equation, it's presumably some type of derived law from a fundamental law. But all fundamental laws are expressed in the form of differential equations. Okay, for example, if you have a ball and the ball is going around, and okay, there is some gravity going like this ball is going with some velocity v, you ask the question, okay, what is the trajectory that the ball is going to follow, and then you have, let's say, some coordinate system like this. This is the position x bar at any given point of time of this particular ball, and you ask the question, okay, what trajectory is the ball going to follow, and you write down the differential equation for the trajectory. It's Newton's second law. You've all probably seen this and worked it out 1,000 times for like cannons and projectiles and things like that. But again, the basic law that governs the motion is this. Okay, and the law has a differential equation form. It has derivatives on the left, it has some function on the right hand side, and finally you have to solve for x. Right? That's what you have to solve for, x bar of t. So that's Newton's law. Newton's second law in mechanics, of course. That's a differential equation. Okay, that's seemingly a fairly trivial example, but still it's a differential equation. You could go to a little bit more, situation that's a little bit more complicated. For instance, I could take a rod and let's say it's attached on the left hand side to a wall, like a cantilever, and somehow I heat the rod from the left hand side. Okay, so I give some heat Q. Okay, and presumably that heat is going to be conducted by the rod. Let's assume the rod is made of some metal, let's say aluminium. So the heat is going to be conducted and it's going to go from the left end to the right end. The right end is open to the atmosphere. There is presumably some air flowing around like this. Okay, and the question you want to ask is, okay, what is the temperature in the rod at any given point? Let's say this is my origin of coordinates, this is y, this is x. At this point P, which let's say has some coordinates x naught, make it one dimensional, and I want to know the temperature at P with coordinates x naught after time t naught, let's say. Okay, how do you find that out? Well, you can do this experiment. Okay, that's one way of doing it. You take a piece and then you stick it up here, and then you heat it, and then you have airflow going on there, and then you look at you put a little thermocouple or a thermistor or something here, and then you measure the temperature, and then as a function of T you can get the temperature at that point. That's one way of doing it, of course. But what if you wanted to know a priori what the temperature is going to be? Okay, then you will have to solve a differential equation. It looks something like this, equals, let me call this some constant A. Okay, it doesn't matter what this constant is, it doesn't matter if you haven't seen this equation before. This is called the conduction equation, of course, and it now has presumably two types of derivatives. You have the temperature at any point is of course a function of T, the T being small t, the time, and it also varies from point to point because heat is coming from this side. Presumably stuff that is closer to the left end, because it's continuous heat input, stuff that's closer to the left end will have a higher temperature, stuff that's closer to the right end will have a lower temperature. So there is a temperature gradient. That's what is driving the heat in the first place. And so the temperature now T is a function of both x and small t. Okay, and this is a standard diffusion equation if you have seen it before, 1 plus 1d diffusion equation in two variables, partial differential equation, and it's still a result of a physical law. Okay, there are two physical laws that are here. There is one that is energy balance, that's what gives you the left hand side, mcp delta t by dou t, if you remember that, if you have seen that before. And the other physical law, of course, is Fourier's law of heat conduction, which says that the heat that is flowing through any particular section is proportional to the temperature gradient across the section. If you combine those two, you will get this equation. Okay. Good. So again, to get the temperature field, you have to solve a differential equation. It's a little bit more complicated than this because it's a PDE, but it's still a differential equation. Okay. Let's take some other examples. And again, physical law, okay, this is energy conservation, this is momentum conservation, okay, that's also some type of conservation law, and all of them, both of them, at least in this case, both of them are expressed in the forms of differential equations. Take another example. I have a pipe and I have fluid flowing through the pipe. Okay, it's driven by, let's say, a pressure gradient across the length of the pipe. Let's say this length is L, this is pipe, and I want to get, let's say at the end of this pipe there is an opening, presumably, and there is water flowing in this pipe. Okay, and when the water reaches the end of the pipe, it's going to fall out in the form of a jet. Now I want to find out what is the velocity at any point along the length of the pipe. That's one question. Let's say this is x. What is the velocity at any length, at any distance along the length of the pipe? That's one question I can ask. What is the shape of the jet that's coming out? That's another question I can ask. Maybe I'm interested in designing a sprinkler of some sort which has to shoot water out to some point, and which should have certain volume of water, which should have a certain shape to the outlet stream, and so on. So then I'll have to ask this question. I mean, the experimental route that we talked about before is now a little bit cumbersome, right? There at least you wanted to know what the temperature was in that rod, and so you could measure it. Now you're designing something, so you have to presumably iterate several times before you come upon something that is useful. So in this situation, solving for the velocity field at any point, again the velocity field will depend on where you are along the pipe a priori, and it will depend on the time. Okay, and so since it has dependence on two independent variables, the governing equation will be a PD. Again, it will look like a diffusion equation in this case, but okay, it doesn't matter. It will be a PD that governs V bar. It's a result from a physical law. What is the physical law? Well, the physical law is that momentum is conserved. So you take any cross section, you do momentum conservation, you write down the equation of momentum conservation, which is written like a differential equation, and you have to put in something called a constitutive law, which is for water at least, which is Newtonian. You can write that the shear stress is proportional to the strain rate. That's a constitutive equation, and you can write the strain rate in terms of the velocity, and then you put all that stuff together, long and short, you will get a differential equation that governs this, a partial differential equation. Okay, again you have a differential equation. So in all of these cases, any physical law, if you're looking at anything fundamental, something that is something that's coming up from a fundamental physical law, again physical principle, then you're inevitably going to come into contact with the differential equation. The corollary of this, or rather on the contrary, if you for example have experimental data for something, let's say I'm measuring A as a function of t, some parameter A, and then I get a bunch of points like this, scatter points from an experiment, and then I fit a curve. Okay, the curve looks like this. This is the best fit curve, whatever curve it is. Then let's say this is experimental points. A is some quantity of interest. It could be for example, it could be the rod, the temperature at that point P that we wrote down for the rod. It could be the velocity at this point, particular point, let's say at coordinate x naught in the pipe. Okay, it could be anything of that sort. I'm just generally denoting it as A. Okay, and I make a series of measurements of A as a function of t. In this case, I could be measuring the velocity. In that case, I will be using a thermocouple or thermistor or something to measure the temperature. And I get these scatter plot, and then I put a best fit curve, and then I get a curve, and the curve, this curve is the best fit curve, and the curve basically tells me A is a function of t. That's what the curve tells you, right? Because you have best fit curve. Okay, presumably if it's like a power law curve or something, then this will be A is equal to k t to the power of b, something of that form if it's a power law. If it's an exponential, it will be a e to the power of bt or something like that. It depends on what type of curve you fit to the data, okay, but you will get a curve. We must make a distinction between a curve like this and a curve you will get for solving a differential equation. And here remember, this is a function of x and t. I am just saying at a particular point x naught, I am going to get a temperature, I am going to get a time dependent curve for v0, for v bar at x0. Okay. This curve is fundamentally different from this curve. Why is that? Well, because this curve comes from some physical laws which are expressed as differential equations which you have to solve and you have to get. This law comes from experiments, of course, so you are not really solving anything, you are only fitting data. So, it is a big difference between that and this in terms of origin, okay. And in terms, okay, philosophically also this is okay, this is more like a theory or a model development type of thing, where you solve a differential equation. This is more like an experimental type of thing where you do the experiment and get the data out of there, okay. Why are they different? Why else are they different? What is the more important difference between them? I am saying V0 bar, for instance, this could be the temperature also, or T of x0 comma T, whatever, right? It could be the physical quantity of interest that we are talking about. Why are these two different? Why else? Okay, the source is different. This comes from some differential equation. This comes from a fit. But why else are they different? To see why else they are different, let's go back and draw that rod. Okay, let's take this for example. Okay, this is a scalar, this is a vector. It can be confusing. Let's take t. So my rod, 1D rod, which is here. This is x. I'm looking at this point P, which has coordinates x naught. I'm heating here, left hand side, whatever, giving some heat Q. I'm measuring the temperature at P, distant x naught from the left hand where the heat is coming in. If I did this approach, I will get a curve for T. Okay. If I did this approach and solve the differential equation, presumably did a lot more hard work, I will again get a temperature as a function of T. Okay, so till now they seem to be the same, right? They seem to be giving you the same physical content. Now remember I said this was aluminium, whatever, aluminium. What if I change this and make this copper? Now you have to go back here, do the experiment again. Okay, because this curve knows nothing about whether it's aluminium or copper. I mean, that's not encoded anywhere explicitly. It is presumably there in the type of curve that you're going to get, but it's not really encoded explicitly. Nothing tells you how A and B are dependent on aluminium. Okay, so presumably that information is not there. So you have to do this experiment again. You will do one more round. You will get T as a function of small t. Again, like this, you have scatter points, blah 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 blah, and then you go like this. Actually, temperature should go down like this because it's heating on the left. Okay, it doesn't matter. Okay, it's like fine. It should probably go up and down depending on how long you put the Q. But we won't get into any of that. Just schematic. Okay, that's all we need for now. There will be a chance for us to solve this problem later on. So you get another curve. So you get a different curve. I'm going to call this T tilde of t. If this was my original curve, let me call it T1 of t. Now I'm going to get a second curve, let's say T2 of t for copper. Okay, good. So I've solved it for copper. Now some guy, you're walking on the street, okay, some guy comes and says, hey, I have a piece of rod, it looks exactly like the other rod you have. Okay, it's not made of aluminum, it's not made of copper, it's made of nylon. It happens, right? Someone could come and say that. I mean, why they would say that is a different matter, but yeah, they could. If that happens, then you're in trouble again because you have to go back and do all the experiments again. You have to do the same thing, put a thermocouple over here, and then you're like, okay, take the data and then do this and fit another curve, and you'll get another 3 of t. And you're happy, okay, there's aluminum, there's copper, and there's nylon, okay, presumably rods can't be made of anything else, okay, which is fine. But then somebody comes and says, hey, wait a minute, I don't want the temperature at P, I want the temperature at Q, which is at a point x1. Could do that, right? And I want it for aluminum, I want it for copper, I want it for nylon. This is more stringent person you meet on the street. Yeah, you always meet them on the street. Now what do you do? Well, you come back and say, okay, Q at a distance x1, okay, let me first do it for aluminum, I'll put a thermocouple here, I measure the temperature, I do best fit curve, I'll get another curve, and then I come back, I change it, and then I put copper, do the same thing, and change it, put nylon, do the same thing, 3 more experiments. Okay, and I'll get in total 3 curves here, aluminum, copper, nylon, 3 curves for this, aluminum, copper, nylon, I have 6 curves. Okay. Now you clearly see the problem with this approach, right? Every time something changes, you have to go back, do the experiment all over again, and assuming this experiment assumes nothing about the fundamental physical laws that govern this problem. So there is no a priori information, you can't exploit any symmetry or any scaling or anything of that sort. It's just a naive go and do experiment type of situation. And if you follow that, you're basically going to be wasting your time. Okay, you're going to be doing this over and over and over again, and you're going to be in trouble. Then next somebody could come and say, I'm changing the cross section of the rod. It's a 1D rod, but okay, I'm changing the cross section, and then now you're in trouble again. On the other hand, if you solve the differential equation, if you get a solution to this, you get a solution for all of these cases simply by changing the parameters that are there in the differential equation. Okay, so now you see the very important distinction between the approach that you take from the experiment, or this type of curve fit type of situation, and what you would do for a differential equation solution. Okay, so this gives you families. It's a little cramped here. Let me write it down here. This gives families of solutions. Not only that, it gives a solution to this. It gives explicit dependence on parameters. So I know what parameters are important now. Okay, if I formulated stuff in the form of a differential equation, I know what parameters are important. I know what stuff I'm leaving out. I know what stuff I'm including. Okay, I know what the approximations are, and so I can tweak those parameters in particular when I change the material, change the cross section, change the heat content, change the boundary conditions, whatever, right? So now I know, for instance, if I went through this entire process, I know that the only thing that matters here is the what is called the thermal diffusivity, usually denoted kappa or alpha or something. And so once somebody comes and tells me this is this bar made of nylons, made of steel, aluminum, copper, whatever, all I have to do is get that value for that particular material constant. I'll put that into the solution that I've got at the first attempt. I'll put that value for the material constant, and I'll get the same output. So I'll get the equivalent of the T1, T2, T3, T4, T5, T6 and so on by just changing the values of constants from a single solution that I've got by solving the PDE. Okay, so that's a very important distinction. I mean, often it's taken for granted, and you think, okay, why do I have to solve a differential equation? I can just go and do this, but really it's not very clever. Okay, and you will run out of space. There are situations where you have no choice but to do this. When the situation is extremely complex, when presumably the physical laws are not easy to write down, and the differential equation itself is doubtful, it's maybe dubious, you don't know if you're leaving out some effects or you're not accounting for certain effects and so on. In those situations, this is probably the only recourse that you have, the only thing you can do, in which case, okay, that's the only option. But whenever you have this option, it's always the better route to take, and you start from the physical principles, you write down equations and you try to solve them. So our aim is not to write down the physical laws. Your courses in solid mechanics and fluid mechanics and thermodynamics and materials and so on will all tell you how to write physical laws. The aim of the next 10 lectures is, once you write down those physical laws in the form of differential equations, how do you get data, how do you get solutions out of it? That's our aim. Okay, so that's sort of a motivation for why you should study differential equations in the first place. And again, you will see that differential equations come up in all sorts of really strange situations, from spinning stars to, turns out zebra stripes. There's something called a Turing pattern, which we won't really talk about explicitly. Maybe I'll give you some references at the end. But all sorts of situations, to populations, to the growth of foxes and viruses and whatnot, all sorts of situations. Okay? Anytime you have a physical law, you have a differential equation. So now we'll have to take one step a little bit forward, and notice I've been saying differential equations all the time without explicitly saying if they're ordinary or partial differential equations. And so we will go and see why we need to study ODEs in particular. That's the content of this section of the course. So we need to understand why we're studying ODEs, or ordinary differential equations. Of course, people know what an ODE is, I presume. I'll write it down for those of you, for those brave souls who don't know what it is. And this is partial differential equation, right? And okay, you know, partial differential equation, you have two unknowns or two or more unknowns. You can have x, y, z, t, multiple unknowns, multiple independent variables. Single unknown, you can have multiple unknowns too. And an ordinary differential equation will usually have just one variable, either t or x or whatever. Okay, we'll usually use t, but you can use x, you can use s, r, whatever, just a single variable. So in this case, you will have to take derivatives. Let's say the unknown function for which you're solving is f. In the first case, f is a function of x, y, z, and t. The second case is a function only of, let's say, t. Okay. So the differential equation relates the derivatives of f in some form to f and to, in some cases, explicit values of x, y, z, and t themselves. Okay. So that's what that is the difference between these two, of course. Now, presumably, unless you have a very specific case, like Newton's law, which we wrote down first, you have a ball that's going and being thrown with some velocity, and then there is gravity acting downwards, and the ball is accelerating downwards, of course, because of gravity is pulling it down, but it's just flying through the air. You want to calculate the trajectory. Okay, how many times in life do you have to do that? Not often, unless you're throwing a stone at someone and you want to be accurate and so on. But most of these situations, the physical laws will be manifest as a PD, as a set of PDs or a single PD of some sort. Okay. So usually physical laws will result in PDs, and remember, okay, we have motivation for studying differential equations per se, but seemingly all the physical laws are going to lead to partial differential equations. So why do we study ordinary differential equation? That's the next level of motivation. So I've motivated you for the first part. Now I have to motivate you for the actual content that we're going to discuss. And the reason is the following. So most PDs can be converted to ODEs by a bunch of techniques, which makes them easier to solve. Okay, instead of solving for a function that depends on many independent variables, you solve for a function that depends only on one. Okay, and how do you do this? Well, there are standard techniques that you will use. For instance, one is via transforms. For example, the Fourier or the Laplace transform. Maybe some of you have seen this before too. Okay. That's a very standard technique in several branches. Of course, it's something called, in vibrations you do it all the time. In hydrodynamics and stability, linear stability analysis, you do it all the time again, without often knowing that you're actually doing this, but it is done. So it's a very common technique. The other, which works very often again, is what is called separation of variables. This you've probably seen before. Okay, so if you have a function that depends, let's say, on two unknowns, PD like this, like our temperature dependent on the distance and the time. I have an f. The separation of variables, if you remember, was like, okay, you write it as a product of two functions. One is a function only of x, and one is a function, use Greek letters maybe, phi of x and psi of t. Okay, so you split it into this, and then you take this. There was presumably a PDE that had f, some derivatives of f, so it had maybe some dou f by dou x and dou f by dou t. Excuse me. Maybe dou square f by dou x square, and so on. You put this form here. The derivatives with respect to x will act only on phi. The derivatives with respect to t will act only on psi, and so one of them will come out, the other one will stay in, and then you can separate the variables. You can divide the equation into two ordinary differential equations. You probably have done this before, and we'll see an example or two later on, maybe in the assignment. And once you do that, you're basically then dealing with an ODE or two ODEs, and you have to solve them separately. Okay. So that's one more situation where this happens. Now notice I said most PDEs. And the reason I said most PDEs is because certainly the PDEs that you can do this for are very restricted in nature, seemingly restricted in nature. They're all linear PDEs. Okay, this is a term we'll use repeatedly, and it's important to know what it is. We'll define some of these terms now in a minute. But only when the PDE is linear, you can do many of these techniques. Reduction to an ODE by separation of variables and so on. There is one other technique. Of course, this is a little bit more obscure, but it is a very powerful technique. It's called a similarity transform. Okay, and that works in very special cases. Of course, it depends on the differential equation that you're talking about. It depends on the PDE you're talking about. But in many cases, you can take some combination of x. If you have, let's say, x and t like this, some function that's a combination of x and t in a certain way, change variables to that new variable, and then you will see that the PDE can reduce to an ODE. Okay, this happens in certain situations. Turns out it happens also for the heat equation, but okay, it doesn't matter. Details don't matter now, but just the fact that you can do this is what is important. So you see, when you can reduce many of these PDEs to ODEs, naturally looking for solutions of these PDEs is the same as looking for the solutions of these ODEs. So it's important to study ODEs in the first place. Okay, that's a very general form. Okay, that's a very general situation that we've talked about. But there are other situations where PDEs, this is a reduction. So you go from a PDE and then you go down to an ODE using one of these techniques. But there are a whole class of other problems which are probably not as well appreciated, which are things called reduced order models, or reduced, this is called them reduced models. Okay, or simplified models, if you'd like. What are these? Well, for example, if you took this flow that you had here, like this, let's say I have a pair of plates that are kept parallel to each other, infinite along the x-axis, and then I send a fluid that's flowing through these plates, and I apply a constant velocity to the top plate, let's say V0, going like this, and I ask the question, okay, what is the velocity profile at this point x? Now this is a two-dimensional problem. Let's say the distance between the two plates is d is non-zero, and so you will have a gradient in the velocity going from the bottom plate to the top plate. Bottom plate is fixed, top plate is moving, so you should have a gradient in the velocity. Okay, this is a complicated problem. Again, it's governed by the same equation as the equation for heat conduction, turns out, the diffusion equation. But you can make an approximation. You can say, okay, if I want to know the solution, but I'm happy if you tell me the solution as t goes to infinity. Okay, so I'm continuously moving this top plate, but I'm not interested in the transients. So presumably transients happen very quickly. Nature of the fluid, I know that a priori, let's say, and I'm not interested in the transition. I only want to know what is the final t goes to infinity, very large t. After a very large t, presumably this profile will be the same here. Okay, what does that profile look like? So then I'm going to ask for velocity profile v as a function of y alone. It's an infinite plate, so as t goes to infinity, presumably the velocity profile should not depend on x, and because t goes to infinity, it should also, if it reaches some type of steady state, again that's a phrase you will hear often, if it reaches steady state, then the velocity should depend only on the y. Of course, the gradient in y will never go away because the bottom place is always fixed, the top plate is always moving with a velocity v naught. Okay, so now I have started with a PDE, but I have made some simplifying assumptions to the PDE. The previous case, I didn't simplify the PDE. I went straight from the PDE, made transforms or change of variables and separation of variables and so on, similarity transforms, whatever. But it was still the same PDE. The content was the same. But now we're looking at situations where the information we need, the PDE contains more information than we actually need, and the information we need can be obtained from the PDE by reducing it down to an ODE. Okay, and notice now this V can understandably be described by some type of an ODE, and it depends only on one variable, just like this. Okay. So these are situations where the laws, the physical laws are written in terms of PDEs again, but then the actual solution of interest is obtained by reducing that PDE to an ODE by getting rid of some terms. So if you look at steady state, then you're basically saying the time derivatives are 0, nothing changes with time. So the time derivative part of the PDE just goes away, and the spatial part that is remaining is what you will get here. Okay, so that's another way you will come up with or end up with an ODE. So you see, it's for a very large number of physical situations, even though you start with a PDE, you're going to come finally and end up with an ODE, and so that makes it very sort of obvious why we should try and study ODEs and the method of solution and how we can get information from them. Okay, so that's another motivation to study ODEs, for studying ODEs in particular. Good. So now that we know that this material is worth studying to some degree, let's actually see how we're going to study this material. Okay, that's what we're going to do. Let's see how we're going to study this. Of course, it's a very big, just ODEs itself is a huge domain. It's got people from all sorts of backgrounds working on it, from numerical analysis to pure mathematics to geometry to topology and engineering, people interested in applications and solutions and so on. So it is a big area, and so we have to try and navigate, find our way through this fairly complex world of just ordinary differential equations by itself. And the philosophy, like I said at the start, that we're going to use is a little bit different. Okay, here's what we're going to do. So what about ODEs are we going to study? Okay, I've told you it's worth studying, so we'll see how to study it. So we'll start with first order systems. First order ODEs. Doesn't matter, linear, non-linear, doesn't matter. If linear first order ODE is trivial, you probably know how to solve it already. But we'll start with first order ODEs, and not because that's the lowest order ODE you can get. Okay? All books will start with first order ODEs, we'll do that too, but for a different reason. The reason is the following. We'll use this to construct some geometric pictures. Okay? First order ODEs are fundamentally important. Okay? You notice that in any textbook, perhaps you never really see ODEs of third order or fourth order being solved explicitly. And there's a reason for that. And the reason is that all the conservation laws, all the physical laws that you write down, from which the PDE and from which the ODE itself appears, all usually contain just second order derivatives. Okay, that's another thing that you will notice. So second order ODEs are presumably more important than first order ODEs. That's the natural way to think about them. but that's not necessarily true. Okay, there are situations where first order ODEs appear. For instance, in Newton's law of cooling, the rate at which temperature goes down is proportional to the temperature difference of a particular object. You've probably seen that law before too. That's a first order differential equation. It's a trivial first order differential equation because it's linear and you can just cross multiply and integrate. But the reason we are interested in first order ODEs is because we can use them to illustrate certain geometric constructs. Okay, and that's what we will motivate this for. What we will also do with this is we will show the relation between nth order ODEs and first order ODEs. Okay, so there's a way to convert an nth order ODE to a system of first order ODEs. We'll see how that is done. It's a fairly straightforward substitution, and it's very important, and that will give you some flavor of what the complexity is when you increase the order of the differential equation. So when you go from first order to second order, okay, presumably just one other additional derivative is there, right? It's like, for example, if I just write down, if I have f as a function of t and then I write down df by dt is some g of f comma t, some function of f and some function of t, whatever. This is a first order ODE. It could be nonlinear because g can be any nonlinear function. It could be f square e to the power of t. That's a nonlinear ODE if g of ft is that. And so, okay, then you go from here, you go to a second order ODE. It looks presumably like this. Okay. The only difference now is being you have the second derivative is some function of the first derivative of the function itself and t. Okay, that's fairly innocuous looking, right? You just have one additional derivative. So you would think, okay, algebraically maybe it's a little bit more complicated than this. Maybe you can't just integrate directly as easily as you could do here. Maybe there are some complications from an algebraic point of view, but that's not necessarily true, and we'll see why that is when we do this. Okay, this is where the starting point will be for this stuff. And it tells us that there is a geometric picture underlying ODEs, which is important to know. It's called the phase space picture, and this will tell us why that phase space picture becomes more and more complicated as you increase the order of the ODE, and then that will give us some indication of what type of solutions to expect. Okay, so that's the way to go about that. Good. Once we're done with first order ODEs, we will go to second order. Again, this seemingly seems like the standard route that people will take, but will be a little bit different. And second order ODEs we will do in the following order. We will first look at linear constant coefficients. Again, this is something you have probably seen multiple times before. We'll quickly just work this out and be done with it. Then we will go to linear non-homogeneous. And then we'll go to nonlinear second order ODEs. Okay, the reason we picked this route is because this goes in increasing order of hopelessness. Okay, there's first order, if somebody gave you a second order linear constant coefficient ODE, you can just solve it immediately. If somebody gave you a non-homogeneous ODE, then you will fumble around a little bit, but you can finally solve it. If somebody gave you a general nonlinear ODE, you are generally in trouble. There's really not much you can do. So it's increasing order of complexity, okay, hopelessness as far as a complete solution is concerned. So our approach in discussing this again will be necessarily because of increasing order of hopelessness, it will be in increasing order of vagueness or more and more qualitative. So increasing of qualitativeness, I don't know if that's a word, but I just made it up. Qualitativeness, okay, whatever. Linear, like I said, you can get complete solutions here. Some cases you can get complete solutions here. Almost no cases will you get a complete solution here unless the solution, the ODE is of a very, very special form. Okay. Now you could go and find a handbook that gives you a list of all sorts of transformations. You make this change of variable, you will convert this into this and then this into this if the form is like this and so on. Those are fine, but they're not very useful. You could always refer to that if you ever come across an ODE that you want to explicitly solve, but they're not worth memorizing, in my opinion. They're worth knowing about, but you don't have to memorize any of that stuff. And so we will necessarily go in increasing order of qualitativeness. Okay. So what does that mean now? Okay. It means that when we start over here, okay, this is more for illustrative purposes because very few physical problems have first order ODEs. So this entire first bit will be for illustrative purposes. When we start over here, we can write down the solution in closed form. Remember what we said about that A of t versus this is the experimental fellow versus the whatever t of t, this was the solution fellow. Solution of a differential equation. Remember what we said about this? We said that in the first case, when you have the experimental guy, it doesn't encode any of the physical parameters of the problem. So there's no way to know how A of t depends on the conductivity unless you do more experiments, right? So the whole point of this, the whole point of having this was to have that type of physical dependence. So you know exactly how t depends on k, conductivity, or on the density, or on the specific heat, and so on. And you know exactly how that functional form is. So that's what gives it the power over this. So to retain that power, you need to have a closed form solution. You need to have a solution that presumably says t is equal to something something as a function of t, which has a bunch of coefficients that depend on the material parameters and so on. That's where the real power is of that thing. You can do that for a constant coefficient ODE. In general, you cannot do that for a non-homogeneous linear ODE. Linear, remember it's still linear. We'll define linearity and so on when we get to this. And you have very little hope of doing that for a non-linear ODE. So you can't get an explicit closed form solution as you go from here to here. So the natural recourse that most people would take would be to say, okay, why are we doing all this stuff? Why don't we just feed ODE into MATLAB or Mathematica? Well, Mathematica is a little bit more complicated. Let's say MATLAB. Mathematica is basically going to do what we're going to do. Why don't we feed it into MATLAB or Python or whatever your preference is? Okay. And get a numerical solution. So you have an ODE, you give it to MATLAB. MATLAB will give you a numerical solution. There are packages that are there, functions in MATLAB that will give you a numerical solution. Why don't we do that? The problem is if you do that, you will get a curve t of t for one particular value of the coefficients. So all that functional dependence advantage that you had over here is gone. Okay. So this naive idea of just taking an ODE, feeding into MATLAB and getting a solution is basically getting rid of the advantage of doing this whole modeling, this whole enterprise in the first place. It's just putting this solution on the same footing as the experimental fellow. Because now, okay, if you want to do different experiments, you have to again repeat the whole thing for different values of aluminum, copper, whatever, like we discussed. You have to do the same thing here. So you have to get, it's presumably some steps ahead of this, because here you don't know anything. There at least you know that you have to measure the conductivity, at least some information. So the effort needed is lesser, but certainly it has less physical content compared to a closed form solution like this. So our preference will always be for, let's get rid of this hopelessness. Closed form solution, that's the first preference. Okay. Second preference will be to reduce to some quadrature. Quadrature means an integral, so you have some integral of some form. You can non-dimensionalize the integral and solve the integral numerically. That's one way of doing it. If this doesn't work, the third step is qualitative analysis, or the third in the hierarchy is qualitative analysis. Okay, so what do we mean by that? We see, okay, how does the function behave when t is so much? When t becomes very large, what happens with the function? How does it behave? Does it oscillate? Does it decay? Does it grow? Things like that. Does it keep cycling? You know, interesting stuff can come out by doing qualitative analysis. That's what you'll see that is the main thing we will do for the nonlinear equations. And if this doesn't work, you try this. If this doesn't work, you try this. If this doesn't work at all for whatever reason, or if it's not giving you any useful information that you want, then you can resort to a numerical solution. Okay, so that's the sequence of sort of conceptual steps that we will take. For this, it's possible to do this. For this, in some cases, it's possible to do this. For this, it's possible mainly to do only this. And if this fails, then you can come and do this for the nonlinear case. Okay, so that should give you an idea of what it is we're going to cover over the next 10 or maybe 9 or 10 sessions. Okay. This is probably the first time I've written more words than equations in a maths class, but it's hopefully served as a good introduction. Good. Okay, so now the motivation is clear. The sequence of steps we're going to follow is clear. Okay. So let's start at the beginning with a first order ODE. I will write down a first order ODE typically, and then we will continue in the next session where we look at some of its properties, and then we look at some versions of it and how to solve it and so on, quickly finish that, and then we'll move on to the geometric constructs that we spoke about. Okay, good. So as a sort of closure to this session, let's look at a first order ODE. I told you have f is a function that is unknown, it's a function of t. This is the independent variable, and f is the dependent variable. Independent variable, dependent variable. Okay. You can often use y and x and y and t and so on. We'll just use this, or we'll also use y of t. That's another way of another notation that you can use. So first order ODE, okay, the most general form looks like this. There is only first order, so the first derivative. It's an ODE, there's only this total derivative is a function of g comma t, or for instance, if you want to write it in terms of some y, we can denote it also like this. Whatever, it doesn't matter. Okay, and g in general is some function. It's a function only of y and t, the dependent and the independent variable, in some form. Okay, it doesn't have to be linearly dependent on them, but it doesn't depend on the derivatives. It could depend on the derivatives, but we assume that you take that dependence out, bring it to the left hand side, take everything together, and you reduce it to this form, and presumably you can do that. Okay. So before we start, there is some formalism that we need to develop, and that is where we will start in the next session. The first question that you have to ask is what? It's a very sort of introspective question, seemingly. The first question is, what do we mean by a solution? What exactly do we mean? When we say solution, what do you mean? Okay. That's the first question. The second question, again seemingly philosophical, is does a solution always exist? Okay, less philosophical, but philosophical nonetheless. And if you guarantee the solution exists, then you go find the solution. Okay. If you're a mathematician, or a pure mathematician, not of the applied variety, then depending on how pure a mathematician you are, you will either stop at this question or you will stop at this question. You will never arrive here. Okay. But since we're all engineers and we need to do something with differential equations in our lives, presumably, this is more important than these two for us. So we will just talk about this briefly when we start next week, and then I'll give you a single statement. It's called Picard's theorem. I'll talk about that and tell you when a solution will exist. And it turns out that for all practical cases, the situations that we're interested in, solutions will always exist reasonably if the conditions or the initial conditions that we talk about are well defined. So we'll sort of give these two cursory treatments and then we'll be done with them, and then we'll start focusing on this. Like I said, there are books written about this. There are books written about these two maths books. They're fairly big and dense. You're welcome to read them. But we will start from here. Okay, so that's where our journey of differential equations will start from.